Okay, this video is the start of a series of 3 on vector differentiation and on coordinate systems. We'll start by looking at rectangular coordinates, but then see how the rules are a little different when we work in other systems such as plane polar, cylindrical, and spherical coordinates. So we'll start with our definition of vector differentiation. Now, vector differentiation is defined in terms of Cartesian coordinates. So say I try to differentiate some vector A with respect to some scalar u. I'm trying to be very generic here. You usually will be differentiating with respect to time. That is defined as the derivative of the x component with respect to u times I hat plus the u derivative of the y component, j hat, plus the u derivative of the z component, k hat. Okay. Now, if we work in other coordinate systems, we'll have to be more careful. Some quick identities. Many of these will look very similar to ones that you've seen in regular calculus. So for instance, if I differentiate a vector sum, it is equal to the vector sum of the derivatives. Similarly, if I differentiate with respect to u some scalar n times a, the chain rule applies here. This will be this will be dn du times a plus n times dA du. So the chain rule still makes sense. And the chain rule works sensibly for the dot product. So d du of a dot b is equal to dA du dotted with b plus a dotted with dB du. The only place where we might need to take just a little more care than normal is with the cross product. And again here, the product rule still works. I want to be clear about that. d du of a cross b is dA du cross b plus a cross dB du. But I mentioned this here because the order of the order of things matters here. We can't just willy-nilly flip the order of the cross product. We do have to do the derivative, and then we have to do the cross product, things like that. So just be a little careful there. Remember, you can't interchange the order of the cross product because the cross product anti-commutes. That would give you a negative value. Alright, so just to get some flavor for how these things get shown, let's go take a look at sorry about that. Let's go take a look at the chain rule for scalar differentiation, for chain rule for a scalar times a vector. Okay, so remember vector differentiation is defined in terms of Cartesian coordinates, so we need to start here d du of n times a. That will equal, following our recipe here, this will be d du of n times a sub x I hat plus n a y j hat plus n az k hat. Okay, now we can go ahead and bring in the derivative. So this will be d du of n ax I hat. So now we're following our rule of vector differentiation, plus similar terms for y and z. Okay, now this in turn, I'm differentiating this bit right here. The chain rule applies. So I will have a dn du times a sub x plus an n dA sub x du times I hat plus similar terms for y and z. All right, but if we follow that through, we can be a little more clever about how we group it. We can go and group all the dn dus by themselves, and then all the n dax dus by themselves. So I'll have a dn du, that'll be times ax I hat, sorry, a sub x I hat, and then when we grouped in from the similar terms, there'd be an ay j hat plus an az k hat. Now, for the other parts, there's a common factor of n everywhere, and that'll give me a dax du I hat plus day du j hat plus daz du k hat. But this last bit here is exactly what we mean by dA dt. So this here is just a, so we are left with dn du times a plus n times dA du, and that completes the proof. Okay, you can prove the other relations in a similar vein, but I will leave those as an exercise. So now let's go and explore what happens when we try to differentiate things in rectangular coordinates. So let's think about, say, this is the trajectory that something is moving on. I've got our origin located out over here. And I'm looking at some position vector r. And then at some later time, the object will now be located at r plus delta r. And the difference between the two is the delta r. So this is what I have to add to this to get that. And you can see that this works by the tail to head rule. Okay, if we go back to our idea of differentiation in general, dA du is defined to be the limit as delta u goes to 0 of delta A over delta u. Okay, so just to make this a little more concrete, let's go ahead and differentiate our r with respect to time. So this will become dr dt. Now, this often gets its own special way of writing it. When you differentiate things with respect to time, physicists often just put a dot over whatever it is they're differentiating. This is a holdover from Newton's notation for his calculus, which I have to say was generally a lot worse than Leibniz's. But this dot is kind of nice, and we only ever use it for differentiating with respect to time. All right, so let's follow this thought through. We're going to be differentiating with respect to time, an x times an I hat, a y times a j hat, plus a z times a k hat. So this will give us dx dt I hat plus dx dy dt j hat plus dz dt k hat. Or we can write that, if we prefer, that our v, or our dot, same difference, is x dot I hat plus y dot j hat plus z dot k hat. Okay, so now if we think about trying to construct a sequence of these positions as our delta t approaches 0. So let's say this is our trajectory like so. We'll go ahead and stick our origin over here. And so here's my first position right here. We'll just call that R. There's my second one. Call that R plus delta R1. There's my third one, R plus delta R2. And then finally we end up over here, let's say R plus delta R3. Okay, so if I was trying to characterize the velocity right here, I would look at a sequence of intervals. So for instance, I would first look at this delta R3. Now that doesn't seem like a very good approximation for what the object is doing right there. So we say, well, let's make the time interval smaller. Okay, that delta R2 seems to be giving me something a little happier. And then this delta R1 would be happier. We could imagine continuing ever smaller, smaller, smaller until we realize that this is going to approach the line on the tangent line. So what we get is that our velocity, v is tangent to the trajectory at all times. Now, if you're being pedantic, you'll notice that I was a little sloppy here. Strictly speaking, when I take the limit, I should have picked pairs of points on either side of what I was interested in and looked as the pairs got closer and closer and closer to the point of interest, but the result is the same. Okay, now we can go ahead and take a look, at acceleration. So acceleration, L-E-R-A-T-I-O, acceleration is dv dt, or d squared r dt squared. Since this is a second derivative with respect to time, this often gets written as r double dot, like that. Anyway, we go ahead and differentiate our velocity with respect to time one more time, and we get that the acceleration is x double dot I hat plus y double dot j hat plus z double dot k hat. Let's make those a little prettier. Okay, I think now is a good time as any to work an example. And one of the things that I always like doing whenever I learn anything new is I try to go back to some example that I understand really, really, really well. And so one of the things that I like to do a lot is to just throw a rock. So let's go take a look at a rock in free fall. Okay, so let's say I've got a ledge here, or some height h above the ground, and I launch my rock up at some velocity c. And let's say that y equals 0 is at the base of the cliff. All right. Well, I think we know the answer, but let's go ahead and do the old guess and check on this. The position is going to be given by ct minus gt squared over 2 plus h, and that's all j hat. Okay, so the velocity would be what I get if I differentiate this once with respect to time. So differentiating this, I just get c. Differentiating this, we'll bring down a 2. That cancels the half. Leaves with minus gt. J hat. Yep, looking pretty familiar. And then hopefully we get the acceleration as minus g, or else it isn't free fall. So let's make sure that works. So a equals, okay, differentiated constant with respect to time, I get 0 minus gt, differentiate t, I get 1, so I have minus g, j hat, and life is good. This is exactly what we were expecting. All right, let's do something a little more complicated, and again we'll guess and check the solution here. So again, I will throw my rock off a cliff of height h, and we'll say that this is x equals 0 here, and y equals 0 at the base again. Okay, now what will be different is this time I will launch it with some initial velocity off at an angle. So we'll say it's bi hat plus c j hat. All right, well, we know from before that the trajectory we're going to take is going to be some kind of a parabola. So let's see if it is. Well, we can look at this we can steal some of our previous work. We know what the y component has to look like. It's ct minus gt squared over 2 plus h times j hat. We did that just before. And we can use our common sense of position equals rate times time to get that the x component would have to be bt times I hat. All right. So then if I differentiate this with respect to time, my velocity, it should be dr dt. Well, differentiating that will just give me b times I hat. And then differentiating the second bit will get me what I had before, c minus gt j hat. And we should double check that, yes, this is still free fall, so we can say that a is equal to dv dt. Well, okay, differentiating b, that's a constant, gives me nothing. Differentiating c, that's constant, gives me nothing. Minus gt leaves me minus g, j hat. So sure enough, it is free fall. If we wanted to know the speed, we can get the speed. That will be equal to the magnitude of v. So that'll be equal to the square of the x component of the velocity. So I'll write x dot squared just so you get used to that notation, plus y dot squared plus z dot squared. So this is what I get if I do v dot v and then take the square root. So now here, the x dot squared is b squared, and the y dot squared will be c minus gt squared, and there is no z component. Okay, so what we'd like to know is where and when is the speed a minimum. Okay, so to do that, we'll have to differentiate v with respect to time and set it equal to 0. Okay, so we'll have to differentiate d dt of b squared plus c minus gt squared to the 1/2. So we'll have to do the chain rule a few times. First thing that will have to happen is I'll have to bring the 1/2 down, and then I'll have b squared plus c minus gt squared to the negative 1/2 there. Then I have to differentiate what's inside. Well, that's a constant, thank God. Now with this bit here, I'm going to have to bring the 2 down, so now I've got a 2 c minus gt, and then I have to differentiate what's inside. That's minus g, and all that is equal to 0. Okay, so let's think about what parts that are a function of time can make this a 0. This term here can never go to 0. The only way that could happen is if c minus gt were somehow imaginary, so that when we square it we get something negative to cancel the b squared. Not going to happen. Obviously the 1/2 and the 2, same deal, and the negative g is a constant, so same deal there. So the only piece we really have to worry about is just this c minus gt, when because it can be equal to 0. So when it's equal to 0 is when our speed is a minimum. So we'll say c minus gt equals 0, and that tells us that we are at a minimum when at a time of c over g. Okay, now strictly speaking, to figure out that this is a minimum, you should do the second derivative test. I'll leave that as an exercise. Trust me, it works. But we can locate the position by sticking in to our position we had before. We'll stick in our value of t and see what happens. So let me just copy what we got right here real quick. All right. So sticking in our result of t is equal to c over g, we'll have that the position is equal to b times c over g times I hat plus c times c over g minus g over 2 times c over g squared plus h j hat. So that's the where. Okay, we can clean this up just the tiniest little bit. Okay, not much. This will be bc over g I hat plus c squared over g minus, okay, now here I'll have is c squared over g squared, but we lose 1 power there. So this will be c squared over 2g plus h j hat, and this can clean up just a shade more to get bc over g I hat plus c squared over 2g plus h j hat. All right. Now, it turns out this does correspond to the top of the trajectory of the object, which is what you would expect. At that point, the y component is 0 of the velocity. Okay. So that concludes the first part of this series. The next talk will be on plane polar coordinates.